Hey there folks, this is JG, and tonight I am playing Oxygen Not Included. This is the first Oxygen Not Included video that I have made, but this is a great little PC game. I have been playing this one on Steam off and on for more than 5 years, I think, at this point. I've been with it since early access. I really remember playing this one while holding my daughter while she was in the NICU. So Oxygen Not Included is a nice little adorable sandbox game. You get dropped on an asteroid with barely any oxygen, and you have to learn to create oxygen and food and all the other things you need to keep your little people alive. So this is not going to be an intro to Oxygen Not Included. So if you're interested, you can check it out on Steam. I highly recommend it. It's a great little indie game. Despite having played this for 5 years, I just recently hit a milestone that I hadn't hit before. I built my first volcano tamer, and actually at this point I've built 3 of them. And so tonight I thought I would show this one off. So just a little while ago I decided to finally build a volcano tamer, and while I was figuring out how to do it, they actually released the new patch, and so it included this conductive panel building, which actually was really helpful to the strategy that I went with. So I think this volcano tamer is going to be built actually in a little bit of a different way than any volcano tamers that you may have seen previously. I will say I did not do a ton of research. I did not look at all the different options for volcano tamers that are out there. I really enjoy trying to figure things out myself for the most part in this game, although I definitely do look up some of the physics details to help me make my plans. So I just wanted to show off the way that I did it in case it inspires you or you find it to be an easy build. And so we'll go through 3 different versions of this that I built tonight. So I built 2 versions for these. I have 2 minor volcanoes. They're actually on the exact same schedule, which I find interesting, but let's talk about what we do. So when you're building a volcano tamer in Oxygen Not Included, the goal here is to extract steam power from geothermal energy. So take the magma that you're getting from a volcano, capture that heat, generate electricity. So there are really 5 key challenges that you're focusing on when you're building a volcano tamer. The first one is you want to transfer the heat into steam. So you need to figure an efficient way to pull the heat out of the magma and put it into steam. Every thermal unit that you get into steam is electricity, and so the more you can extract, the better. The second challenge is you want to control the transfer rate of that heat, because if you heat up the steam too hot, above 200 degrees, it actually caps out the power of a single generator, and so your efficiency drops. So you want to keep the temperature under 200 degrees, but usually fairly close to 200 degrees so that you're generating a good amount of electricity. So you want to extract a lot of heat, but not too quickly. One of the simple ways to do this is just dump water on top of the volcano and a bunch of really hot steam comes flying out. That's usually too hot to work with, and although it'll help cool down things pretty quickly, it's not the best way to get a large amount of electricity. Challenge number 3 is that all the buildings that you're using to construct this volcano tamer, you don't want them to break. You don't want them to melt, and you don't want them to overheat. And so when built with steel, which is your best option before you get into space materials, your overheat temperature is going to be 275 on a lot of these. And so definitely 200 degrees is good enough for the steam, but if things get much hotter than that, you're going to be facing buildings that need to be constantly repaired. That's going to be a big headache for you. And then the final 2 challenges are about the igneous rock that you get out of this. So as the magma cools, it turns into igneous rock, either as debris piles that fall onto the tile or as solid igneous rock tiles. And so if you're talking about the igneous rock debris, you want to be able to manage that debris. You also might want to use that to feed to a hatch farm to turn into a sustainable source of coal or something like that. If instead it's turning into igneous rock tiles, you need to prevent that from clogging the volcano, because if those tiles build up on top of the volcano, then it won't be able to erupt anymore because it's full. So those are the things that you need to deal with. So the thing I was inspired by when I saw this conduction panel that they released was, what if instead of transferring the heat from the magma directly into water by bringing them into contact with each other, what if we run the volcano in a vacuum? And what that does is prevent the magma from transferring heat to general surfaces nearby, but it only transfers via conduction to solids or liquids that are in contact with it. So we're not getting any gas-related conduction. The reason that's really helpful is because that means all these buildings in here that are used to keep the setup working, they don't really have any heat problems. They get none of the heat from the magma. If you ever built some of these buildings in space or in vacuums in other places before, what you figured out is although the conductivity of nearby things doesn't pose a problem for them, their own heat generation does. So this 2000 DTUs that a RoboMiner generates, it takes a while for that to build up, but eventually, no matter what material you build it out of, it will overheat because that heat can't go anywhere. The vacuum both means that it can't receive the heat from nearby hot surfaces, but it also can't vent that heat to nearby surfaces. So that's where this liquid conduction panel comes in. So if we look at the setup here, I've got liquid conduction panels on all the key buildings here that can generate any heat. So that includes the RoboMiner. Its job is digging out solid tiles if we ever get solid tiles in here. You've got the sweeper, whose job is to lift out the igneous rock debris when the time is right, and the conveyor loader, which is how it then gets outside to the real world. Now, the rest of the setup is around creating a nice conductive channel for the heat to make it all the way into this heat chamber. So if we look at the steam turbines themselves, pretty simple setup. We've got this hot metal floor. We've got a sealed amount of steam. As you usually do in a steam setup, the water output just dumps right back into the room to be reheated. So that 95-degree output water feeds back into the system. So we've got a stable amount of steam. And that's where we generate the power from. So let's talk about this setup right here. So one of the first things I tried was just this stack of steel tiles. So everything in here is built with pre-spaced materials. So steel, ceramic, and obsidian and diamond are the only materials that I'm using here, as well as some igneous rock. So nothing that's too hard to obtain. So my first solution was just have these metal tiles, and they pop up this stack here to conduct the heat all the way into the boiler chamber. These airlocks here, this is a pretty common technique, I think, for managing things. When airlocks are open, they don't conduct heat. When they're closed, they do. So when these close, that makes it a highly heat conductive link. Then we open and close these airlocks on a circuit, basically a temperature circuit. In this case, I put these two little thermosensors inside the build. They're kind of close to the heat source, and it's basically just a negative feedback loop. So we've got a memory automator here, a memory toggle. One of them, when the steam gets too hot, it turns it on. When it gets too cold, it turns it off. Basically modulates the airlocks being open and closed based on that. So the first time that I built this, what I noticed was the magma that was directly in contact with the metal here would be the fastest to cool, because this metal, it sort of conducts heat in two directions. It conducts the hotness from the magma up into the steam. It also kind of conducts the coldness from the steam back down into the magma. And so what you'd have is the magma here would turn into debris, and the magma here would still be hot. And by the end, let's see, with the temp shift plates, it would be these two tiles would turn solid while we still had hot magma over here. And so I realized, we need to keep something conductive in contact with all of these tiles. You can see I built a bunch of diamond temp shift plates, but again, those transfer tile to tile. They don't transfer tile to debris or building to debris. And so these built tiles will transfer to the liquid tiles nearby, but once the igneous rock turns into debris, it's sitting here on top of neutronium, none of the heat is moving. And so while we don't want a gas in here filling up the tiles, because that can transfer the heat all the way to the rest of this. Liquids work really well. And so the liquid that I realized is a great fit for this is lead. So what I did was drop a bunch of lead. Actually, that's why this conveyor chute is sitting here. I had a little automation for manually dropping lead into the room. I put a few thousand kilograms of lead, and lead has the great property. Its freeze point is 327 degrees. Now, the turbine here can cool things down if you let it go for long enough, all the way down to about 125 degrees before it stops. So 327 is a bit away from that, but honestly, since things are coming out of this at 1726 degrees, cooling it down to 327 before the whole system solidifies and stops working is really pretty fantastic. So as the igneous rock turns solid, I think you saw it earlier in the video, we saw an eruption cycle. You have magma sitting on top of lead, and they transfer heat just fine to each other. The magma also transfers directly to like these higher steel tiles. But then as it solidifies, we get this igneous rock debris. You can see this is still at 1080 degrees right now and dropping. Since it's immersed in this nice bath of lead, it is transferring heat into that lead at a nice high rate. Lead, being a refined metal, is nicely conductive, so it pulls the heat out of all the igneous rock that's sitting inside of it and transfers it pretty effectively through this pile of lead and into the steel and into the rest of the system. So I found this to work pretty nicely. The next challenge is it only cools down the igneous rock to about 500 degrees. We can't let it stack up in here, or maybe we can, but my fear is if I let too much rock stack up, then as it erupts, it starts giving me this low quality, 500 degree igneous rock instead of, you want the really hot stuff, because the hotter it is, the more efficiently it transfers the heat. And so that's where I ended up building a stage 2 system here. This auto sweeper, the circuit I have it set up on, basically a chain of filter gates where if these airlocks stay closed for a long period of time, that means we're just not getting a lot of heat out of this quickly. That's our signal that this whole system is cooling down too much. And so that's when these filter gates kind of slow it down and say, 300 seconds after, if we get 300 consecutive seconds of closed airlocks, then go ahead and turn on the auto sweeper here. It dumps igneous rock into here, and it comes all the way up here into my second stage boiler. And so this one I run slightly differently. I basically dump igneous rock directly onto iron metal tiles. It's usually about 500 degree igneous rock to start with. So we put it in direct solid contact, debris sitting on top of metal tiles, also sitting in the steam directly. So this one is not a vacuum system. But here the goal is just extracting the last of that heat out of these. So cooling them down from the 500 degree range all the way into a range that's a little safer for duplicants to handle. And so you can actually see here, I built this kind of complicated, it's 8 different chutes, and I just basically split evenly among them. Similarly, I split the water coming from above into those. That's basically to increase surface area. The more surface area you have, the more separate tiles you have transferring heat from the rock to the steam or the rock to the iron. So once we get to 500 degree igneous rock, we throw it in here, we start cooling it down a little bit further. I tried a couple different ways to detect when this one was getting just about done. One of the challenges is sometimes it can't cool the rock quite fast enough before more eruption cycles start. So I have this auto sweeper in here that basically just at all times is taking this rock out. And I have this final third stage processing system. I keep cold water, actually in this case it's fairly warm water, it's 44 degrees. And I just take the hot igneous rock out of here, run it in circles through the water until it hits the point where it is below 50 degrees. That's sort of acceptable for the rest of my base to use. It finally exits that loop here and drops into a pile. So this final step here is just this final cooling water. You can see We're cooling that water continuously. So in a lot of these places, you can see I've got thermo aqua tuners inside the boilers themselves. In general, once you're ready to do steam power, this is where you want all your thermo aqua tuners so that you're recapturing heat. Thermo aqua tuners don't really remove heat; they just move heat. And so you want to move them into a place where you want heat, which is inside your boilers. And so basically the cooling action of this water is turning into additional heat power into this turbine chamber. So that is my initial setup. I have this neighboring small volcano that I mentioned is on the exact same setup. So this was my V2 setup. It's pretty similar. So again, vacuum right in here. We got this circuit for the auto sweeper. I've got the robo miner in there. Pretty much same strategy in here. Again, obsidian and ceramic tile to sort of throttle the heat transfer. Very similar strategy, moving the heat over here. I will say one thing that I learned, I have these liquid locks in place in a number of places so that I can still put my duplicants inside here if I need to repair anything. I usually keep a door at the front with access turned off, but although I hoped this would be a completely hands-off system, really I've learned that I make mistakes every once in a while, and I need to get in and kick the system and get it working again. And so leaving those gates to sort of get in and out is helpful. This one I did a little bit different. Now, after all that, I got kind of cocky, and so then I went up to these larger volcanoes. So this is a Badlands map that I am playing on. I put the map seed into the video description if you want to see it, but there's lots of volcanoes around here. So what I saw here, let me show you what these look like. I've got one in the wild that I haven't tamed yet. So yeah, you get some of these. In this case, it's a pair of volcanoes surrounded by liquid magma, surrounded by hot obsidian, and then, of course, surrounded by abyssalite, so it's safe until the time that you decide to go in and start working on it. And so I wanted to harvest one of these, but obviously with that existing liquid magma all around it, it doesn't need to be excavated yet. And as soon as you start digging into that, you've got magma flying everywhere, and you've got the volcano starting to erupt before you're ready. And so here I developed a nice method for constructing this system from scratch. And you can see that starting right over here. Let's see. So this is one of the ones that I'm still cooling down to make useful. So what I did is just built a couple of steam turbines and then a boiler room, and just filled this up with water, and then kind of cracked the edge of this open. So I just sent in a few people to dig past the abyssalite and into the obsidian layer. And so in this case, I really haven't built these turbines for electricity. They're here for heat reduction. Their job is just to cool this whole system down. So put in a lot of water. In this case, the steam, 50 kilograms per tile, so it's very dense in here. But it's just picking up tons of heat. This stuff was 1,000 degrees when I started. You can see it's at 130 degrees now. And so obsidian is fairly conductive, so just being in contact with that obsidian, I've let this go for probably a couple hundred cycles, and after a little while, it turned all of this liquid magma that we saw around the volcano into just hard igneous rock. So now this thing is clogged up again, and we can fairly safely dig it out, build all these structures around it before we finally dig out the last tiles and make it start erupting. And so the twin in its system is the one that I've succeeded in harvesting here. So I actually did manage to dig that out. Since this is a full volcano, I put in 4 turbines up here to capture the heat. And I built a little bit of a different style this time. So in this case, again, we've got the vacuum chamber. I actually hid the robo miner and the auto sweeper underneath it in this case. Built one ceramic tile up here. So in this case, I actually do still have some magma that just sits on the top. But as it erupts, it drips over the sides and onto a metal plate here. So and this time I used tungsten, a very high melting point, and very good heat conduction, and a little bit cheaper to produce than steel. So I wasn't burning all my steel in this setup. So really similar, same idea. We've got the lead in here to help capture it. The whole thing is sitting on metal, which helps pull the heat a little bit more evenly from all the parts here. I initially, you can see I have this really thick 3-tile, tungsten block conducting the heat upwards and into these airlocks and into the system. That initially was just one, and what I realized was I wasn't actually keeping the boiler room hot enough. The challenge that I was seeing was, although tungsten is highly conductive, and the steel doors here are highly conductive, with the large amount of heat that I needed to get through the system, I wasn't able to cool everything down fast enough. So I needed actually more points of connection here. I still haven't been running this one long enough to know if I'm fully cooling it. I haven't fully set up yet the auto sweeper here. It doesn't really go anywhere. I haven't turned this on. I've got it just on a manual circuit at the moment. Or no, it's on a built circuit, but I haven't set up the filters on the loader because I'm not ready to take the igneous rock out yet. But it does look like it's getting a lot more heat. The meter on these turbines is staying a lot higher when now that I have this triple wide conduction system here. The last thing I'll mention for cooling the turbines themselves, if they get above 100 degrees, they stop working and they absorb some of the heat that they're taking out of the rest of the system. So in all of these systems, I have one aqua tuner that's just dedicated to cooling the system down. So I used polluted water as my coolant. Since we're potentially getting up to 100 degrees here, regular water has a small risk that it might, boil over and create problems for you. And so polluted water has that, a little higher operating range. And so I just pipe it through a combination of radiant pipes and more of these conduction panels. So we're cooling it down. I have a little bit of an intelligent circuit here so that, we've linked a liquid valve to a liquid temperature sensor. So when it's warm enough that it's not going to freeze, we'll send it back through the aqua tuner to get cooled down further. Otherwise, we just sort of loop it with itself, keep cycling it through that system and cooling everything down. And so in steady state, oh man, these are a lot colder than I would have expected. Maybe we're late in our eruption cycle. Yeah, the turbines are nice and cool. And of course, all the heat that we generate from that goes back into the boiler, which is useful. Yeah, a lot of these run a lot hotter than that. So these run about 40 degrees, which is very comfortable to not be overheating while the system's running. So that's it. That's my first tamed volcano setup, and using the new conduction panels to allow the whole system to run in a vacuum. I think it's fairly compact here. You don't need a whole lot of additional space other than a little, few blocks around the volcano and then a boiler room. And for this Badlands map, it helps me get a lot of electricity out of this abundance of volcanoes that I've got here. So that's all I've got tonight. Let me know in the comments if you'd like me to do more Oxygen Not Included content in the future, or if you have any other Oxygen Not Included topics that you'd like me to cover. That's all. Joji out.